In this video, we'll be discussing the difference quotient. The expression f of x plus h minus f of x, all divided by h, for h not equal to 0 is called the difference quotient. This expression has real significance when we get to calculus, so we're developing our algebra skill now so that we can apply it later. Let's find the difference quotient of each function. Here our function is f of x equals 3x squared plus x plus 5. Anytime your function is a polynomial, I recommend you do the difference quotient in parts. Start by finding just f of x plus h. So we'll be replacing all the x's in our function f with the quantity x plus h. And then we want to simplify. We have a binomial squared right here. So we want to write that twice and multiply it out. We can drop the parentheses around the second x plus h because there's nothing but a plus sign in front of it. Multiplying out those two binomials, we get x squared plus xh plus xh plus h squared. We'll distribute the 3. You could combine the like terms inside the parentheses first and then distribute the 3. I'm just choosing to distribute the 3 first, and then we'll combine like terms after that. This gives us 3x squared plus 3xh plus 3xh plus 3h squared plus x plus h plus 5. Looking for like terms to combine, we have these xh's here that can be put together. 3x squared plus 6xh plus 3h squared plus x plus h plus 5. So that's the f of x plus h. The difference quotient is f of x plus h minus f of x, all divided by h. So we're going to take this expression that we just found, plug it in here for f of x plus h, and then continue with the rest. So our difference quotient will be 3x squared plus 6xh plus 3h squared plus x plus h. Now we need to subtract f of x, which was our original function. Be sure to put it in parentheses because we're subtracting this whole function. And then all over h. We can continue to simplify the numerator by distributing the negative and combining like terms. Looking for like terms to combine, we have x's, x squareds, and constants that can be combined. And you'll also notice when you combine these like terms, each pair cancels out. So we're left with 6xh plus 3h squared plus h all divided by h. Our difference quotient definition said that h could not be equal to 0. So we want to simplify this even further. When we get to calculus, we're going to be finding the limit of the difference quotient as h approaches 0. Basically, we'll be plugging a 0 in for h. If we plugged a 0 into this expression for h, we would have something that was undefined because we would have 0 in the denominator of a fraction. You want to continue to simplify the difference quotient until that h in the denominator cancels out. Notice that there is a common factor of h in the numerator. We can factor that out, which would leave us with 6x plus 3h plus 1 all over h. Now that our numerator and denominator are both in factored form, we can cancel common factors. So we can cancel that h out, leaving us with 6x plus 3h plus 1. This is our difference quotient. And you'll notice now with our result, if we did plug 0 in for h like we're going to do in calculus, that middle term falls out, but we're not left with something that is undefined, which is the concern. Let's look at another example. Let's find the difference quotient of g of x equals the square root of x minus 1. Here our given function is not a polynomial, so I would be comfortable just doing the whole difference quotient at one time. Our difference quotient is g of x plus h minus g of x all over h. I encourage you to write this formula every time you do a problem until you have it memorized. G of x plus h, here we're going to plug x plus h into our function everywhere we have an x. So that's x plus h minus 1. Now we subtract our g of x, which is the square root of x minus 1, and that's going to be all over h. The reason that it's not necessary to do the g of x plus h separately when your function's not a polynomial is because there's little to no simplifying to do. In the previous example, we saw there was a lot of simplifying to do for f of x plus h. Here, there's none. Looking at this expression overall, I don't really see any simplifying that can be done. My radicals aren't like, so I can't combine them. There's not an h that I can factor out. But this can't possibly be the answer, because if I plug a 0 in for h, I have something that's undefined. We're going to apply an algebra technique that we know, but in a different way. We're going to rationalize the numerator of this expression. Since the numerator has two terms, we rationalize it by multiplying the numerator and denominator by the conjugate of the numerator. The conjugate of the numerator will be the square root of x plus h minus 1 plus the square root of x minus 1. And we'll do the same to the denominator. Remember that the conjugate is the exact same thing, but the middle sign has been changed. Also recall that when multiplying conjugates, the middle terms always fall out. So all you have to multiply together are the first two and the last two. If you have trouble remembering that shortcut, well then do a full FOIL, no big deal, and you'll see that the middle signs fall out. I'm going to take the shortcut, multiplying just the first two together, the square root of x plus h minus 1 times the square root of x plus h minus 1 leaves us with just x plus h minus 1. When multiplying the last two together, notice that we have a negative times a positive, so I'm going to have minus whatever I get. The square root of x minus 1 times the square root of x minus 1 is just x minus 1. It's very important that you have that x minus 1 in parentheses. We'll ultimately have to distribute the negative. In the denominator, we want to multiply h by the conjugate. Frequently, we would distribute the h, but in this case, we don't want to. Recall what our objective is. We want to be able to cancel that h in the denominator. The only way that you can cancel things when you have a fraction is to cancel common factors. So we want to leave our denominator in factored form, which would be h times the square root of x plus h minus 1 plus the square root of x minus 1. We'll distribute the negative in the numerator and combine like terms. X plus h minus 1 minus x plus 1 over our denominator. Combining like terms in the numerator, I have x's that are like, but notice they fall out when I combine. Also, I have constants that are like. They also fall out when I combine like terms. This gives us h over h times the square root of x plus h minus 1 plus the square root of x minus 1. My numerator has a single term. My denominator is in factored form. Therefore, we can cancel the h's out. This leaves us with 1 in the numerator and the square root of x plus h minus 1 plus the square root of x minus 1 in the denominator. Although there is still an h in our denominator, it is not going to cause an undefined expression if we plug 0 in for it. Our difference quotient is right here.